Good morning. Here it is, Tuesday, the 9th of October, and I am still at home. So, hopefully you are watching this during class time, because that's what I plan on instructing you in the email that I'll send once I've got this video posted. So today we're going to talk about a new statistic, but now we got to make sure we have a really good understanding of that last z-test, because when we learn this new statistics, it's this much different than the one we already know. Okay, so I'm actually going to start out with an example of a z-test. Okay, so I'm stepping back to before the exam so that we can get a full understanding of that z-test. So here's an interesting example. Okay. A drug company wants, whatever. A drug company knows that people's average time to fall asleep is 17 minutes. That's the average mu, with a standard deviation of 4, and that's sigma. They've created a new sleep-enhancing drug that they believe will help people fall asleep faster. They give the drug to a sample of 20 people, and on average, these people fall asleep after 15 minutes with a standard deviation of 3. Did the drug lower the time required to fall asleep? Okay, so we've got a situation here where we've got, let's review now. We have a known population, okay? The population has a known mu, 17 minutes. It has a known sigma, 4, okay? So these are knowns. We have a single sample, and we would like to compare our sample to this known population. So these are all the requirements necessary to do the z-test. Okay. So step one, let's talk about our hypotheses. Okay. Now clearly, my job is to market my drug, and so I'm not talking a two-sided t-test, no t-test. I'm not talking about a two-way test, because it's like, what good is my drug if it takes longer to fall asleep, right? I'm only interested in faster to fall asleep. But be careful, the word faster, which is a kind of a strange word, literally means smaller time. Okay? And so with this one-tailed test, remember the easiest, most logical thing is to always think of the alternative hypothesis first. So the mu, or the average number of minutes to fall asleep with the drug, is less than the average number of minutes to fall asleep without the drug, right? I mean, that's literally what the alternative says. And so, of course, the null hypothesis says the average number of minutes to fall asleep is either larger than or exactly the same as the average number. In other words, the alternative hypothesis is stating my drug makes people fall asleep faster. The null hypothesis states my drug either does A, nothing, or B, makes them take longer. Okay? So all possible outcomes in the world must be incorporated. Step two, let's set a region of rejection. Okay? So now remember what we're doing is, in fact, if you take a quick look here, there we go, alpha equals 0.05, okay? One tail. And so since we're looking for faster, or, faster, we're looking for a smaller mean, smaller than the average, right? And so in this case, remember what's going to happen is in our z distribution, it's split down the middle, remember, with 0.50, or half the distribution off to the left. We want to know the far left 0.05, but remember, because of the nature of our chart, we need to look up that 0.45, because our chart only tells us distance between score and mean. So recall that, and I'm going to come back to this chart and look for a 0.45, and lo and behold, I won't find a 0.45. Of course I won't. I mean, we've found that over and over and over. But we find a 0.4495, a 0.4505, where I've circled there. And so our answer is exactly in the middle between those two. So if we come down the left side to 1.6, go over to 1.64 or 65, whoops, it's right in the middle, 1.645. Whoops, that should say negative. You see that? That's supposed to be negative on that thing. Boo-boo on my picture. So you see it there, you know it's a negative because it's to the left side of, right? It's on the left. It must be a negative. Shame on me for not putting it there. Step 3, compute this test statistic. We know we compute a standard error, right? sigma sub x bar, and we take the original sigma sub x divided by the square root of the sample size. So we get the original sigma of 4, right there, 4, the original sigma of 4, divided by the square root of the sample size. Sample is sample of 20 people. See, there it is. Okay. And so sigma sub x bar equals 4 over the square root of 20, or 0.894. Okay. So now we'll take this new standard error, or sigma sub x bar, and we'll use it to calculate an obtained value of z. Okay. So of course the z-test has us take the sample mean minus the population mean over the standard error. So sample mean, here I go, 15. You see my sample is 15. The population mean was 17. Right? And so there it is. 15 minus 17 over 0.894 is negative 2.24. And so now let's make a quick step 4, or evaluate the null hypothesis. Remember, our only two options are to either accept the null, no wait, see, I didn't say that. Is either reject the null or fail to reject the null, okay? That's it. Now, someday when you get into your experimental class, we'll talk about, why it is this way. It'll, we'll explain it better, but you never make a decision in terms of the alternative. Always in terms of the null, you either reject it or you fail to reject it. That's it. That's the only two options. And so in this case, we look at our obtained value of z of negative 2.24, and you look at the z critical we had there of negative 1.645. We see that the obtained value is in fact in the region of rejection, so we reject the null. And perhaps far more importantly, we come to a conclusion. The drug makes people fall asleep significantly faster. Okay? So remember, that word significant is a powerful word. You can only use it if you have gotten to this point and your obtained value is in the region of rejection. Now you have permission to use the word significant. Okay? If you haven't done that, you don't own that word. You can't touch it. Well, we did. Okay. So it's a simple example, and we'll take this example and I'll repeat it again once I get to the t-test. I'll just I'll change some of the scenario a little bit, but we'll take this same example. Okay. Whoa, we already did. What did I do? Wait a minute. Oh, because it's going up there. I got it. Okay. So I want to talk about something now that's completely new. So we've talked about the z-test. I mean, we gave a nice little sample example, whatever, of a z-test. But now I want to talk a little bit about these things called assumptions. Okay? All statistical tests have assumptions. And so I want to start out on this, and from here on out, every single time we talk about a new statistic, we're going to talk about the assumptions. Now, each test has their own assumptions, but they share an awful lot of assumptions in common. Okay? And so let's start with the first one, the single sample z-test. So here's the thing. This is kind of an interesting little side note on statistics. You can do any damn thing you want with numbers, okay? You can whip them in, you can do this, you can that. But if you have not met the assumptions, remember, say, for example, we had talked about if your dependent variable is measured in the nominal scale, you could take nominal scale data and put it into a z-test. It'd be absolutely gibberish. Your interpretation, the statistic wouldn't care. It would run it. It wouldn't care what the hell you put in there. But if you tried to use nominal scale data in a z-test, interpretation would be just outrageous, okay? So this is kind of what's going on. If you haven't met these assumptions, you can run the test. The statistic doesn't care what you have, but when you get to that last part and try to make a conclusion, it's a gibberish conclusion. You violated all the rules. So these are just sort of the things that need to be true in order for you to make those statements. Remember, the statement that really, really counts when it comes to this statistic here is the drug makes people fall asleep significantly faster. And if you haven't met these assumptions, it's a meaningless statement. Okay, so number one, the sample that you draw must be a random sample. Okay, it should not be, and again, when you get into an experimental class, we'll talk much more heavily on different sampling techniques. But for random sampling basically means, you put all possible scores from the population into a hat, shake up all the names, and pull them out. Again, and this is more of an experimental thing, but it's an assumption. Independence of observations. And this is going to be an assumption that is true of all statistics. I can't even imagine a statistic around where this is an assumption. Independence of observation means if you have two different scores, or for example, the people in this test falling asleep, right, on our sleep test there, two different scores cannot be related to each other. That is, the outcome you get from one score cannot influence another score. If I don't know how to do it. Maybe, I guess, if you had 5 people in the room at the same time and they were interrupting each other's sleep patterns, then you don't have independent observations, right? Because each of those 5 measures are related to each other. So you need to have independence. It's kind of a strange thing. There's an assumption that the value of sigma, okay? Because remember, what we did was we rejected the null in that last example, and we said there is a mu, and there you go. No, that's not a good one to show. There is a distribution of times to fall asleep, and we have said that there is a completely separate distribution for time to fall asleep after taking the drug, okay? We have said there's 2 different distributions here of sleep times. One distribution of sleep without drug, one distribution of sleep with drug. And the idea is the value of sigma for both of those distributions needs to be the same, okay? If you had a sigma of 4 in the original population, then the sigma for the distribution of sleep time with drug should also be 4. Okay, that's an assumption, but again, this is real hard. You can't do some. Most people kind of just roll over these assumptions. I'll be honest with you. Most people don't really take these assumptions all that seriously. We need to understand what they are, though. And then the last assumption is the distribution of sampling means is normally distributed. And now this 4th assumption, I hope that we can say, hey, I can just roll right past that one, and that's only because you got to go back to chapter, I don't remember which lecture, but where we learned about the central limit theorem. Because the central limit theorem, if you recall, says, and the distribution of sample and means will approach a normal distribution as the size of the sample increases, as the size of n increases. Anyway, go back and review that one if you don't know what I'm talking about. So you don't need to worry about this. As long as, take a look, we have a sample of size 20. That's a pretty decent sample. And because there's a sample of size 20, it is definitely assumed that the distribution of sampling means will in fact be a normal distribution. Okay, so now here I am. I put up a presentation about this last week, but I think it had 4 views on YouTube. It wasn't pretty. So I'm going to go through this again because one of the things I'm going to have you do is a lab assignment, okay? I have given you everything you need to do the lab assignment on, I believe it was called statistical hypothesis testing, but I'll put the details in the email I'm going to put together for you, okay? So let's kind of go through some of these bigger things. This is it's the same presentation as I had on YouTube the other day. Review that one because that is a good one. But this, I'm just going to use kind of different words, but the same idea, okay? So our main goal in hypothesis testing is to determine whether our sample mean is very likely occurrence from the distribution. It sounds weird, but in other words, the original population was, I'm going to go back to the example I just had, okay? The original population is time to fall asleep without a drug, okay? We already know the mu of that was 20 and the standard deviation was 4. And we believe, because we rejected the null, that there is a separate distribution, right? A separate distribution of times to fall asleep with the drug, okay? So now, whenever we make a decision about the sample, we always do so in terms of the null, right? Remember, reject the null or fail to reject the null. And so remember the deal. If a sample mean is very far away from the untreated population mean, we reject the null and say it came from a different population. Take a look. Our sample, look at that. No, it wasn't this one. Our sample is at that z of negative 2.24. And so we said, look, our sample is very far away. Because our sample is very far away, we've decided that this sample I've drawn belongs to a separate distribution. Okay, we made that decision. We rejected the null. Okay. If the sample mean is near the untreated population mean, in other words, if our z obtained had been like negative 0.1, that would have fallen in the region of non-rejection, and we would have failed to reject the null, right? So that's our only two choices, reject the null or fail to reject the null. When we do this, reject or fail to reject, different things can happen, okay? And in fact, hopefully, I'm just going to, let me see if I can see what's in this one. Hey, where are you? I'm going to come back. Where is it? Hopefully, this image is familiar. It should be if you watch the video. Where am I? I want to have a video right here. If you watch the video I put together last week, which only a few of you did. But if you did, this slide should look familiar. And so I'm going to talk some words that will build up to a better understanding of this slide. Okay. With a type 1 error, what happens is, if you reject the null, remember, if you reject null, the null means nothing. If you reject nothing, you think something. Got it? So a type 1 error is you reject a null when it is actually true. Okay? Again, going back to our example, let's say the drug does not actually help people fall asleep faster, but I came to an incorrect conclusion that in fact it does. Okay? That's really what this type 1 error is. And it can occur if the researcher failed to use proper randomization in some way, drew a sample that was in some way different. And so all of a sudden, what happens here is, let's say, for example, given what our sleep example, maybe I drew a sample of people that really what kind of a sample would I get? Let's say I drew a sample of people that were good sleepers. I don't know why this is true. A sample of really good sleepers, and I gave them my drug. They fell asleep faster than average, and I say, oh, the drug made them fall asleep faster. And it's like, no, you just drew a bad sample, dude. You didn't get a truly random sample. You got fast sleepers for some odd reason. Okay, and so if this happens, and so when we make these errors, and errors will happen, by the way, they will. This is the cost. Underneath my head here is the cost. If this happens, then I, the researcher, will make a false claim. And I'll say, hey, my drug works. And then people will spend time and money trying to replicate my results. They'll, perhaps if I'm able to market my new sleeping drug, people will waste money buying a product that does no good. Okay, that's what a type 1 error literally is. Wasted resources. People are spending money on crap that is just garbage. Here's an interesting example. Okay. I created an SAT study class. I gave the class to a sample of 50 people and find that their average after taking my class is 592. We know this isn't true anymore, but we're going to have to go for it. I then calculated a single sample comparing, we have to have an imagination because I remember in one of these recent slideshows I looked it up. But imagine the SAT score has because it used to, by the way, this is why I have it in here, right? That used to be the truth. Has an average of 500 with a standard deviation of 100. That was true of the SAT for many, many, many years, but recently they've done crazy crap to it. And so I gave people an SAT study class, 50 people. They had a 592. I looked at this sample average of 592 and I go, holy crap, that's really far from 500, okay? And so let's say I run the z-test and I'm going to get a z. You could do it. I mean, I've given you all the information you need to run the z-test, but I would estimate, let me see, square root of 50, what was it, 100, square root of 50 is, so that's, yeah, the obtained z would be like 5, okay, something like that, maybe 6. And so if the obtained z is positive 6, that's going to be in a region of rejection. It doesn't even matter what, you know. You can do the math on it, though. I mean, go for it. What do I care? Okay? And so here's the deal. Two things. I've rejected the null, okay? Now that I've rejected the null, there is two possible things that could happen. Number one, my class really does in fact raise SAT scores, and I have in fact correctly rejected the null. I've done exactly what needs to be done. But the other possible thing is that I made a mistake. It's possible, maybe for example, I took this SAT class and I put up a flyer and I was like, hey, come on in and take my class. And only motivated people did this. People that were like, my God, they were on the ball. These are kids that really had their shit together. And so all of a sudden what happens is, maybe because these kids were real motivated kids, my class didn't do anything. Even if they had never taken my class, they would have scored 592, right? What they got. It wasn't my class, it was because I had motivated students. And I committed a type 1 error. So when I reject the null, it is possible that I have correctly said that my test made a difference, or it is possible that I have made a type 1 error and falsely claimed that I made a difference. Okay? Two possible outcomes. One good, one not so good. With a type 2 error, if I fail to reject the null, and it was supposed to have been rejected, okay? And so in this example, maybe what happens is, going back to the sleep example, okay? So I put up a flyer for, I need people to participate in the study where I'm testing whether or not I can make you fall asleep faster. And here's what happens, okay? People that are having really hard time sleeping sign up for my study. Got it? Because, damn, they have a hard time sleeping. They take my drug, and then what happens is all of a sudden, remember the average time to fall asleep way back at the beginning was 20, and all of a sudden, let's say this group of people takes 20 minutes to fall asleep, and I'm like, my drug did nothing. See, my sample came in, and my sample took 20 minutes to fall asleep. The population average was 20. My drug didn't do anything. But the fact is, these were people that have a hard time falling asleep. These dudes would have taken 47 minutes to fall asleep. My drug brought them back to 20. Wow, that's a big deal, right? And so what happens is I made a type 2 error. I should have. My drug really does make a difference, but I have failed to find that. And so what are the costs of this? I lose out on potentially very valuable treatment option, okay? And so all of a sudden, I'm incorrect. And so going back to the SAT again. Again, we're going to pretend it has an average of 500 with a sigma of 100. And so what happens, okay? I gave this class to a sample of 50 people and find that their average score is 508. Now, clearly, if the population average is 500 and my sample mean is 508, I don't know what the z test would come up with, like 0.8. I don't know, I'm guessing. Again, you can do the z test if you really feel like it, but the z obtained would be about 0.8. And there's no possible way a z obtained of 0.8 will ever fall in a region of rejection. It just isn't going to happen. And so given this scenario, I would fail to reject the null. And so again, it's very possible that I have the two different outcomes if I fail to reject the null is, one, my class doesn't in fact do anything and I have correctly stated to fail to reject the null. I've made a good choice. Or, as I said, my sample was kind of not very smart. That's why they took my class, okay? If they hadn't taken my class, they would have scored a 427. I brought them from 427 up to 508, looked at the 508 and said it's not different from 500 and said, fail to reject the null. So you get the idea is when we reject the null or fail to reject the null, there's basically two outcomes in both cases. You made the correct decision or you made a mistake. Gotcha? Or error, rather. Okay? So it's pretty straightforward here. And it's summarized up on this table here, or chart, or whatever you're going to call it. And so Here's what happens in hypothesis testing. Okay, when we are, because remember, we're doing a statistics class here, but the statistics that we talk about are part of a larger research process. So never forget that there's a bigger research process involved. And so a researcher is often, interested in figuring out what is, you see on the far left there, what is the truth of nature? What is it that is true about the world? And again, in this sleeping example, there's two possible truths that are out there. Either this drug does help people fall asleep, or this drug does not help people fall asleep. Okay? Or I'm going to flip that around. Either the drug does not help people fall asleep, right? The drug does nothing, the top row, or the drug does in fact help people fall asleep, the bottom row. Okay? It's just to keep those clear. And so you can see what happens is we can decide to either reject the null or fail to reject the null along the top. And so if we make these outcomes, right, at the top row, there is no relationship, the drug does nothing, and wait, the null is true. Yeah, the drug does nothing, and I reject the null. I made a mistake, type 1 error. So you're going to have to go through this in some more detail for the lab exercise, which I'm going to make sure you get done today. Okay? So I want to talk about these errors a little bit, okay? Because when we do hypothesis testing, here's the problem. I mean, and I've told you this before, statistics. I am an experimental researcher and I study human decision making. And we can talk about strategies to help us make decisions, etc. And one of the strategies that we use to help us make decisions are statistics, probability, right? Alpha equals 0.05. You've kind of got a handle on that alpha 0.05 thing. And so this statistical hypothesis, whatever. In fact, look at the very title at the top of the slide, decision making. So statistics are just a way to help us make decisions, okay? So if you ever take some of my upper level courses in something like cognitive, you'll see me talk about different decision making strategies, and probability and hypothesis testing is just one in a long list of strategies that we can use to help us make decisions. And so when we make decisions, any kind of decisions, we can make mistakes. We always can make mistakes. We're never 100% correct. And so these mistakes here with type 1 and type 2 errors, okay, are difficult. As I said, type 1 errors and type 2 errors have costs. Remember, the type 1 error, the basic cost is I've said my drug works, the drug doesn't work, and so people waste money buying a drug that doesn't work. A type 2 error, my drug does in fact work, but I've said it does not work, and a potentially very useful medicine has been lost to the world. Okay, so these are the real world costs of type 1 and type 2 errors. And so when you're designing your research, you have the ability to control how many type 1 and type 2 errors you're going to have. Okay? You have some control. Number one, we can see right here the probability of a type 1 error equals alpha. You see that right there. And remember, alpha equals 0.05. There it is, okay? 0.05, 5%. You can see it. And so given this notion of alpha equals 0.05, oh my gosh, where did I go? Given the notion of alpha equals 0.05, I can literally tell you the probability of committing a type 1 error is 0.05. All right? It's straightforward. And when I wrote that example, I could have said alpha equals 0.01, right? Type 1 error would be 0.01. But when you make this decision about alpha 0.01, alpha 0.05, whatever you might want to make it, you're not just making a decision about type 1 errors, because the relationship between type 1 and type 2 is quite powerful. Okay? So the first thing we need to say is anything that makes a type 1 error less likely will make a type 2 error more likely. Okay? And so check it out. If I said alpha equals 0.05, and then I said alpha equals 0.01, If I change from 0.05, at 0.05, I'm going to make 5% type 1 errors. At 0.01, I'm going to make 1% type 1 errors. Lovely. I've made fewer type 1 errors when I went to 0.01. But when I went from 0.05 to 0.01 and lowered type 1s, I raised type 2s. Okay? So we need to look at these costs and figure out, you're going to make mistakes. I need to balance these two. So a little more on that relationship. Okay? Anything that makes a type 1 error less likely will make a type 2 error more likely. So as the probability of committing a type, yeah, feel free to read that. I said that. So now we can mess around with this, and there we go. I'm showing you that the words right here as you change from 0.05 to 0.01, etc. And again, in medicine, they feel that a type, okay, looking at these two, in medicine, I've got a new cancer drug, okay? A type 1 error is, again, a false claim about how good the treatment is. A type 2 error is losing potentially valuable medicine. And so in medicine, they looked at it, and they usually set the type 1 error rate to alpha equals 0.1, or they will make 10% type 1 errors, because they believe that the real-world cost of a type 2 error, losing out on valuable cancer medications that could save lives, is too big of an error to make, and so they are willing to accept 10% type 1 errors to make up for it. Okay? You get the idea here. These errors have real-world costs. Okay? I'm somewhere. Oh my God, where am I? There we go. These errors have real-world costs, and it's our job to think about what the costs are and how I want to balance them. Okay. Yeah. All right. In fact, what I need to show now is the four different results in this chart here. I've already said as type 1 errors go up, type 2 errors go down. Direct relationship there. But guess what? Let's just stick to the top row. If type 1 errors go up, then the box that says 1 minus alpha goes down. And you look, it's a direct relationship, alpha and 1 minus alpha. It's absolutely perfect relationship. If you increase type 1 error by 0.05, you decrease correct by 0.05. It's absolutely straightforward. If you look at the bottom row, the type 2 errors and the bottom corner correct are also direct. One is beta, one is minus beta. And so again, if you do something to increase the type 2 error rate by 0.05, you'll increase correct by 0.05. I mean, it's really straightforward, or decrease correct, or whatever I'm trying to say. A very, very direct relationship. Well, this bottom corner box, the one that's called power, is by far the most important one. Okay? Power, as a definition, I wonder if I have it defined on this slide somewhere, because I really like the word. Power, the probability that the test will correctly reject a false null. This is a very big word, okay? Just like that word significant before, the word power is a word that has a very, very specific meaning and should only be used in the proper context, okay? The power of a statistical test is defined as the probability that it will correctly reject a false null. Take a look at where power is. You see the corner? It's at the intersection of the null is false, the null is supposed to be rejected, and we in fact reject the null. Okay? And so power, the power, right? Again, the words are the probability that the test will correctly reject a false null. If there's something that should be found, if the drug does truly work, will I come to the conclusion the drug works? That's what power is. If there is a reason I should reject the null, if there is a reason that an effect should be found, will I find that thing? And so experimentally, we can do things to manipulate power. Okay? But since, as I've now explained, all four of these boxes are related to each other, as I do things as a researcher to manipulate power, all the other ones are going to change, aren't they? right? Because they're all related to each other. So to manipulate power, here's what we do, okay? Power is affected by these 5 things. The size of alpha, okay? Whether or not we choose one-tailed or two-tailed tests, and again, this is just a play on alpha, and I'll kind of sort of describe that. The sample size we use, the effect size we have, and the amount of variability in the raw scores, okay? So I'll explain this kind of briefly. And again, here's just a couple of the same thing. The larger the alpha, the more likely we'll be able to detect a false null. In other words, coming back to this chart, okay, kind of a weird thing. If I raise alpha, in other words, type 1 error, if type 1 errors go up, type 2 errors go down, power goes up. You see the relationship there? So type 1 goes up, type 2 goes down, power goes up. Okay? So it's a real simple thing that the larger the alpha, the more likely we will, and so we can find it. A one-tailed test increases power. Because in a one-tailed test, remember what we're doing is if you have a one-tailed test, alpha is 0.05, all of your 0.05 goes into a single tail. But if you have alpha equals 0.05 two-tailed, remember we split it up and put 0.025 in each tail. And so really you're just playing, this slide is just a manipulation of this one. By changing from a two-tailed 0.025 to a one-tailed 0.05, you're just simply raising the alpha level. It's just really, for all practical, or decreasing the alpha level for all practical purposes. So don't sweat it too much. Where are you? There you go. As n increases, we've seen this as the n, or in this case, remember the size of the sample, right? And again, from our sleep example, we had a sample of size 20. As n increases, the distribution of sampling means gets thinner and tighter and tighter. And we saw this one in multiple cases in that sampling distribution lab assignment that we managed to get before I got sick. So as sample size goes up, the sampling distribution of the means get thinner and thinner and thinner. And as the sampling distribution gets thinner, trust me on this, power goes up. Okay? The effect size. The effect size is interesting. This is something, again, don't forget, statistics is not a standalone thing, and it's a shame that the statistics class is in fact being taught separate from the research methodology class, because they just cannot be thought of as separate things. And so as you're designing your study and you want to test, does my new sleeping drug help people fall asleep faster? And you do the study with like, you give them 5 milligrams of the drug, all right? And you don't find anything because, dude, it's only 5 milligrams, okay? Instead, you give them 30 milligrams of the drug. That's what I mean to say increase effect size. If you want to test whether or not a drug works, if you use 5 milligrams, you would have a small effect size. If you use 30 milligrams, you have a large effect size. And so as effect size gets larger, power goes up. Okay? And again, you, the experimenter, while you're designing your research, have the ability to do this. You're in charge here. Okay? And this last one is a little bit strange too. Minimize variability in the raw scores. All right. In other words, we did a sample of 20 people that we brought into our laboratory. We need to take the sample of 20 people and treat each and every one exactly the same. Okay? Because if I treat them differently, and for one of those 20 people, the room is really cold. Well, duh, if the room is really cold, that one person takes longer to fall asleep, right? So you need to make it such that every one of your, again, our first example, every one of the 20 people coming in for your sleep study is treated identical. The better you can treat them exactly the same, the smaller the variability in their scores will be, the higher the power. Okay? So it's five things now. 1, 2, 3, 4, 5. 5 things that affect power. Okay? You can affect power by messing with alpha, messing with how many tails it has, how large your sample size is, how big the effect size is, and the amount of variability. And so these are, as I say, these are beyond statistics. These are a step before statistics in the process of data gathering. Okay? Okay, where am I? Yeah, here I am. Okay, so we're going to move on to the single sample t-test now. So we've kind of talked about, we had an example of the, what am I saying? Hey, where are you? We had an example, again, in the z-test, we had a situation where we had a known population average, a known population standard deviation, and a sample that we would like to test whether or not it is different from that population. Okay? So now, when that was true, that we knew mu, sigma, and a sample, then a single sample z-test was the appropriate statistic. Okay? Today we're going to talk about something a little different. We're going to have a scenario where you know the population mean, mu, but you just don't know the sigma. You just don't have it. And so what's going to happen is you've got a known population mu, but you don't know its sigma, but you've drawn a sample. And you will be able to calculate a standard deviation on the sample. In other words, S sub x. We're going to use S sub x in some kind of strange way. Remember in the z-test, we needed the sigma in order to calculate the standard error. If we don't have access to the sigma, we cannot calculate standard error. Instead, we can calculate an estimation of the standard error. Okay? So that's kind of what we're going to do here. We've got a situation now where since we don't know sigma, okay, we're going to do the best we can. We're going to use the sample standard deviation as our best guess of sigma. So here is the deal. If you have, in fact, here's my original example. Given this example, I have a population mu and a sigma of 4. Got it. I have a sample that I'm comparing it to. A z-test is appropriate. However, as you see, I've given you the sample standard deviation in this example of 3. Because I gave you the sample standard deviation of 3, you could calculate a one sample t-test. Okay, it's possible, absolutely. But the z-test is preferable. The single sample t-test we're going to learn today is an estimation of the z-test. So if you have the ability to calculate a z-test, calculate it. The only reason I'm going to go to the t-test is because I don't have any choice, okay? Because I have not been given, oh, I know you're on here somewhere. Wow, we really went far here. Okay. So because I don't know the sigma, I'm going to guess and use the t-test. I would prefer a z-test if possible. Okay? And so there was our calculations. But look at this from the z-test. Since I'm talking about a situation where I don't know sigma, the very first thing there, calculating standard error, is a dead end, right? We won't be able to calculate the standard error. So let's try this example. It's the exact same example, but look what I wiped out. Pretend we've got the exact same thing, and we know the average time to fall asleep is 17 minutes, mu, but we just don't know that standard deviation. And so I have a new sleep drug, I gave it to 20 people. Everything else is exactly the same, but now I just don't know sigma. Okay? So given this example where I just do not know sigma, let's try it. Okay? But again, otherwise everything exactly the same. So lo and behold, a single sample t-test, guess what I did to create this slide? Copy and paste. It's the exact same slide as the z-test. There's no reason that this would change in any way, shape, or form, okay? The alternative is the drug helps people fall asleep faster. The null is either no change or worse, right? I mean, exactly the same. But now we have to do something a little bit funky. Setting the region of rejection, okay? We're estimating the z-test, gotcha? We want to do the z-test. We would prefer to do the z-test, but we just don't have the information necessary, so we're stuck with the t-test, okay? Keep that in mind. And so what's going to happen is that when we look up our critical value to set up a region of rejection, we need to look in not the z-score chart, but in a t-score chart. And a t-score chart is literally an estimation of a z-score chart. I mean, it's for all practical purposes, okay? So let's take a look here. A t distribution is similar to a z, okay? It's a frequency distribution. It's shaped very, very much the same. Its exact shape is off of the z, okay? And it turns out that the t distribution is different from the z distribution, but it depends upon something called degrees of freedom. We're going to talk more about degrees of freedom as the semester moves on. But for now, a single sample t-test has degrees of freedom of n equals, degrees of freedom equals n minus 1. In other words, the sample size minus 1. And so again, for our example here, whoopsity boopsity, hey, something weird is happening over there. For our sample size, we have a sample size of 20, and so what we've got now is going to be degrees of freedom of 19, n minus 1. So let me take a quick look at what the T chart is. This chart, it's a PDF document in the Lecture 8 folder on Blackboard. So make sure you go and get a copy. You know how to hit pause, right? Get a copy of this thing, pull it up. I would have printed it out and handed it out to you today if I was in class, but hey, it's up there. It's a PDF. And so take a look at this chart, and I've circled the most important pieces of information for us. So when looking at this chart, the first decision we have to make is, am I looking at a one-tailed or a two-tailed test? Okay? Aha, it's a two-tailed test. Wonderful. Now, I stick to the one-tailed test row. Move over to, what was the alpha? Alpha was 0.05. Move to the 0.05 column. Okay? Now, moving down the far left side, degrees of freedom, what do I got? 19. Aha. With 19 degrees of freedom, one-tailed test, alpha 0.05, our critical value, or that value that is going to set off the region of rejection, is 1.73. Or more specifically, because we are all sophisticated now, negative 1. Oops, I jumped a chart. Negative 1.73. Okay, because we were, remember, faster time to fall asleep. And so you see what I've got here is, you know, this distribution that you're looking at, for all practical purposes, it looks like I drew a z-score test, or a z distribution, and it basically is, okay, the higher the degrees of freedom. In fact, how about this? If degrees of freedom equal like 1, you know, some crazy low number like that, this distribution would be almost flat. Remember Platy-Kurtic distributions that we learned about in Lecture 2 or something like that? It would be Platy-Kurtic. It would be so flat, it would be crazy if you had degrees of freedom equals 1. But if you had degrees of freedom equals infinity, then all of a sudden this t distribution would be the z distribution. It would be exactly the z distribution. Okay? And do I have it here? No, I chopped it off. Okay, it would be the z distribution. In fact, if you look at, I can't show it because I chopped it off here, but if you look at the very bottom row of this chart, I would imagine the very bottom one on the degrees of freedom says infinity. I don't remember. They usually do. I don't remember this exact one, but I hope it does. Because if it says infinity on the degrees of freedom at the very bottom row, then you should start to see some familiar numbers looking across. Remember, like the 1.96, the 1.645, the 2.33, some of those numbers we were working with at the z-test ought to be popping out in that bottom row, if in fact it says infinity. I don't remember. Like I said, most of the time they have that last row for infinity, but maybe not. Okay, so we're sitting here with the degrees of freedom 19. For all practical purposes, as far as I care, it's shaped essentially like a z-distribution. Okay, and so using the exact same logic as before, now that I've got this critical value, look at that. I put negative 1.73. If I had been clever, what I would have written was, remember, just like the last time I put like z sub crit, right? Well, this one should be t sub crit, right? This is a critical value of t. We are now going to do a t obtained, right? Just like we did a z critical, a z obtained. Well, we have a t critical, and now we're going to do a calculation for t obtained. But otherwise, same, just a slightly different distribution. And so here's what's going to happen. Because we're using our sample standard deviation to estimate that sigma, we're going to calculate an estimated standard error. Okay? Just like I said before, I wish I could have a standard error. I would prefer to have a standard error. I just don't have the information necessary to create a standard error, so I'll do the best thing I can do given the limitations of my numbers. I will make an estimated standard error. And it's the same calculation, except now it is the sample that I drew, 20, sample of size 20, fell asleep 15 minutes, x bar equals 15, with a standard deviation of 3. Okay? And so lo and behold, it's the 3 over the square root of 20 and get 0.671. Then we'll calculate the single sample t-test. And again, now I have it there, t obtained. I meant to put t critical on that last slide, but here I go, t obtained. And wow, look at how familiar it looks. Score, the sample mean minus the population mean over the estimated standard error. Okay? 15 minus 17 over 0.671, negative 2.98. And so, wow, I would hope that it should sound familiar, because I'm going to take the obtained t of negative 2.98 and compare it. Does negative 2.98 fall in the region of rejection? Why, yes, it does fall in the region of rejection. Because the t obtained falls in the region of rejection, we conclude the drug makes people fall asleep significantly faster. We came to the same conclusion here, but it's absolutely possible I could come to a different conclusion because my region of rejection has now changed on this t-test, right? So very cool idea, what we have here. So this new t-test is not new, okay? Again, I'm just going to give a quick repeat before I move on to the last couple of slides. I would rather do a z-test. The z-test is the bomb. I don't know if kids use that word anymore. The z-test is the bomb. But I can only do the z-test if I know the population mean and I know the population sigma. If I have those two pieces of information, Daddy does the z-test. Okay? I'm only doing the t because I have no choice. T is an estimation of z. It is not my preferred choice. It is what I do only because I ain't got the right. I'm missing the information needed for the z-test. Therefore, I'm stuck with the t-test. Okay? So that's what we got. That's it. It's otherwise exactly the same. So here we go to a kind of a different idea. Now, this is not different. This is something we've seen repeatedly. We can take our sample mean with the drug and make a point estimation of the population with the drug. Okay. We learned the best guess, if you have a sample mean x bar is the best guess we have of the population mean mu. And I'm sure you remember that slide from lecture 3, and it said x bar is an estimation of mu, right? It's the best estimation. We call this a point estimate, okay? If I had a sample mean of, in this one, what was it again? The sample mean of 15 minutes. I have a sample mean of 15 minutes, and you pressed me, and you said, hey, baby boy, what did I do here? Where did it go? I just moved it somewhere. Well, you saw it. I moved it somewhere. Yeah, whatever. And so we're going to have to pretend I didn't move that slide. Okay. So if I said the sample mean was 15 minutes to fall asleep with the drug with these 20 people, what's your best guess? If you could give that drug to every person in the world, what's your best guess of time to fall asleep? 15 minutes. Okay. It took 15 minutes. I guess 15 minutes. Okay. Now, what we want to talk about is something called confidence intervals. And confidence intervals, you guys already know these. I'm positive. I mean, you know this idea. Because I'm absolutely positive that if you pay attention with politics the way it's been in your face lately, especially now with the midterms coming up, I hope you listen at least a little bit. Because what you'll often hear is like, the average voter, 57% of the voters said they'd vote Democrat, whatever. I don't know what the numbers are, okay? With a margin of error of plus or minus 4, okay? Perhaps you hear that margin of error, and they keep talking about, the differences between the margin of error, blah, 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 blah. And every time they use this funky margin of error, they're saying, okay, my best guess is that if we took all the Democrats in the world right now and had them vote if we took all the voters in the world in America, bite my tongue, take all the voters in America and have them vote right now, my best guess is 57% would vote Democrat. But I recognize that that won't be exactly true. That's just my best guess, okay? And so I'm going to say that what I had said was 57 with, a margin of error of 4. That I guess 57, but I'd be willing to bet that the true answer is probably not exactly 57, but within the error of 4, in other words, 53 to 61. I'm very confident that even though I'm guessing 57 as my best guess, I'm really confident that it's between 53 and 61, plus and minus 4. And so that's the idea here, okay? So again, the mu with drug, right, in our example, my best guess is 15, right? My sample mean of 15 is the best guess of the population mean, 15. But what we're going to do, and I'm not going to do a lot of details on it, I want you to get the idea behind it far more than I want you to do the calculations on it, okay? And so you see what I'm going to do here is I'm going to take the mean of 15, I'm going to take the standard error and the critical value of t, okay? Where did I get that t crit from? Oh, I know why I had to do that. Yeah, I know what I had to do. I remember. I had to get a different value of t crit. In this case, I had to pull a two-tailed value of t at 0.05. Yeah, there it is, 2.09. Is that what I said on this next one? Boy, I'll look stupid if I'm wrong on that. Yeah, that's where I got it from. Okay, you see what I did here is I needed to take the two-tailed 0.05 and get 2.09 because when I do these confidence intervals, I'm going in both directions now away from the average. So I needed a two-tailed. Yeah, whatever. Like I said, I'm not that concerned you know how to do this mathematically. I'm concerned that you understand what the heck it means, okay? And so take a look here. I'm going to calculate this thing and say the mean of 15 plus or minus a standard error, estimated standard error of 0.671 times that critical value of 2.093. So it's 15 plus or minus this value here. And so what we find is, look at this, 16.404 and 13.596. In other words, given our study, if you pushed me and said, okay, your sample had an average time to fall asleep of 15 minutes, what's your best guess if I could possibly do the entire population and give them this drug? 15 minutes. Well, I'm probably going to be incorrect. So I'm going to say I am 95% confident that if I gave the drug to the entire population, the population mean would be between 13.84 and 16.16. That's what it comes to, is that we make a point estimate with the mean itself. My best guess is 15. Confidence intervals are to say but I'm 95% confident that the true answer is between these 2 points. Okay? That's really what it is. And again, that's really what in political polling what margin of error is all about. Okay? Is confidence intervals. That's it. All right. And so the last slide I have here is the assumptions of a single sample t-test. And since the single sample t-test is really just an estimation of the z-test, these should be awful familiar. You must have independent observations. I promised you earlier that's going to pop up everywhere. And the population that you sample from must be normal. And again, we don't really care about this one because of the central limit theorem. Remember the central limit theorem, which says it doesn't matter what the population. I wish we could have got that one computer simulation to work that day in the classroom, but it doesn't matter what the population of raw scores looks like. The distribution of sample means will approach a normal distribution as sample size increases. Right? Again, that's lecture 6 or something. I don't remember. So the second assumption is really not that important. All right. So if I have the ambition, I might put together a couple more examples of some t-tests, or maybe I'll save them for Thursday. Who knows? We'll see how ambitious I am. So I will see you on Thursday. I'm banking on that.